Hello and welcome. I am Dr. Anil Joshi. Welcome you to my series Learn Radiology with Dr. Anil Joshi. Today we are going to learn radiophysics. By and large, it is considered as a complicated, but once you go into our series and see multiple videos, we have made it such simplified that even one or two hearing will be perfect, make you perfect as far as that particular topic is concerned. Now today's topic, this lecture's topic is characteristic radiation. Now radiophysics is important because once we know the radiophysics, then only you can make best use of the techniques available like MA, MAS, KVs, and that will give you better image. And unless we get a good image, we cannot give a good interpretation. So let's get going to the topic. Now first is definition. Characteristic radiation is produced when a high speed electron from the X-ray tube, that is from the filament, ejects an inner shell electron, usually K shell, of the target atom, that is commonly tungsten. An outer shell electron, when drops into the inner shell, because it has to fill the vacancy, outer shell is extracted now to fill this vacancy, and in this process the difference in this energy level is emitted in form of X-rays, because as we know the energy cannot be created or destroyed. It can just change from one form to another form. Then why it is called characteristic? The energy of the emitted photon is unique to the atomic structure of the target material. Hence, a characteristic of tungsten, the most important transition is from the L shell to K shell, producing a K alpha line. So, that is very important to understand K alpha line, and that is responsible for the characteristic radiation production. Now, what is the threshold energy? The characteristic radiation is only produced if the incoming electron has sufficient energy to overcome the binding energy of the inner shell. Is very obvious, na? Even it has to displace certain electron which is on its path, it should have more energy than that. For example, 69.5 kV for tungsten in a K shell. Now what is its role in imaging? The characteristic X-ray contributes to the discrete peak in the X-ray spectrum. The important is higher kVp settings, that is more than 70, especially in CT and in general radiography. It is useful in mammography when molybdenum or rhodium targets are used to optimize the contrast. What we do in a mammography tube, we use high MA and low kV technique for the soft tissue contrast. They produce high contrast pictures. Now this is required in mammography tube versus in routine conventional X-rays. When we need kVs of around 70 and more, we need Bremse-Strahlung radiation. Now what is the Bremse-Strahlung radiation? It is a continuous spectrum. Most of the beam, during its passage, it produces a uniform kV X-rays. Now what is the characteristic? They are discrete peaks and may be material specific. If you use different material, they will be different. So it is material specific. Now let us come to today's topic, because the other type of radiations are covered somewhere else. It contributes only to a small fraction of the photon in an X-ray beam as far as characteristic X-rays are concerned. When an incident electron ejects an inner electron from the tungsten target, an electron from the outer orbit is quickly attracted to the void in deficient inner orbital shell. Since there is deficiency, it falls inside. When the outer orbital electron replaces the displaced electron, a photon is emitted with an energy equivalent to the difference in the two orbital binding energies. Clear? The energies of the characteristic photon are discrete because they represent the difference of the energy levels of the electron orbit level, hence the characteristic of the tungsten atom only. If you use something else, it will be something else. Now this is the diagram which shows you incident high energy electron is bombarded, then there is a recoil electron, a vacancy is created that is filled by the outer shell electron, and a characteristic radiation is produced. Now it is important to know the electron of the inner shell has got more kinetic energy or the high energy level as compared to the outside. So when the displacement occurs, there is liberation of energy. So again, more characteristics of the radiation are from the diagram. Now here what we are seeing is a filament which produces electron with the help of boil-out effects. They are attracted towards a cathode. The potential difference accelerates them. The cathode is made up of tungsten, and because of its characteristic, it produces the radiation. Now let us understand the tube design so that we will understand how the X-rays are produced. Now X-ray tube principles. There is a filament which is heated. Electrons are released, which is called boil-off effect, that is thermionic emission. Here they can be evident. You are seeing from hot filament how the electrons are boiled off. Now once they are boiled off, now they have to focus. So for that there is a focus cap. By focus cap, they are streamlined into a single direction towards the target. Now the target is anode is positively charged and the cathode is negative. So that produces potential difference which accelerates speed of electron, and they go and hit the target. Now here they are suddenly decelerated, and this deceleration causes X-rays to be emitted. So here we are seeing electron fast moving, then they hit the positively charged anode. Now different designs are made according to the requirement of this. Now the positive voltage applied to the anode is related to the filament electron acceleration towards the target. That basic aim, they should be targeted, they should be accelerated, and they should hit only the area which we want. Now they gain the kinetic energy because of this potential difference, because of the energy they are getting, they become more energetic. The electron structure, these highly charged or highly speed electrons, they hit the target. The electron, whichever kinetic energy they have got, it gets converted into heat and X-rays. So these are the two things that can occur once suddenly they are decelerated. Now what is the role of electron? Now this is a tube design. You are seeing that electron carries high energy as a kinetic energy. For two, one thing is their own energy, plus they are accelerated because of the potential difference between anode and cathode. So they are with high energy level. And because of that, they have got more speed. They move faster than electron. And these electrons are controlled by electric field. Means more the potential difference you apply, more will be acceleration and more will be high level X-rays or photons. X-rays are nothing but a pocket of energy or called as photon. Then what are the requirements to produce X-rays? A filament voltage you have to apply. For that, because of that, there will be thermionic emission, electrons will be expelled. This electronic cloud will be attracted towards anode because of the high potential difference between two. See, high voltage source is applied to accelerate them. So filament voltage and high voltage. Now what a filament voltage does, it gives more thermionic emission, more electrons available, and what high voltage does, more potential difference. faster speed. So more electron, more speed, more X-rays. In that way it works. Now this is a cathode filament. This is the X-ray tube. We have shown it in a diagrammatic manner. Now this is the hot filament which is emitting the electrons. Is a coil of tungsten wire, simple thing, like you are seeing in the bulb. Similar to a light bulb or a filament, cathode is a source of the electron. Filaments are heated by the electrical current, they are attracted, they are accelerated, and then they are decelerated. Now how the X-rays are produced? Here we are seeing it in a practical X-ray unit. We got kV, we got MA, and we got X-ray tube, which in detail we are going to see. The X-ray produced by the two distinct processes. One thing is characteristic radiation and Bremsstrahlung. These are the two phenomena, either characteristic or a breaking radiation. So these two forms a radiation. Now here characteristic radiation we are seeing. Now interaction of high speed incident electron with orbital electronic target are required to produce characteristic radiation. Then electron from the filament removes inertial orbital electron from the atom. It is same as what we have seen just now. Electron from higher energy shell cascade down to fill the vacancy. Now this will liberate characteristic radiation. Now here we are seeing the characteristics of it. It consists of only discrete X-ray energies. The energies correspond to the difference between the electron shell of the target atom, specific energy characteristics, and target material. So with the help of these simple diagrams, which are made a little bit interesting so that you will not find this lecture complicated, I have made this lecture in extremely friendly way. I hope you have understood. I hope it will be useful to you. With that, we are coming to the end of this lecture. Thank you, goodbye, and take care. We'll meet again in next video. Till then, take care.